Now we're going to do the collision resolution techniques, which are basically techniques for hashing, or for preventing collision in hashing. So what is hashing basically? It is basically mapping some values to some respective indices, right? So for example, and the indices are basically going to be some array, right? So this is my hashing table, but it's basically an array, right, in which I'm putting my values, right? And for the 12, I'm going to find the index in which I need to put the 12, and I'm going to do that using a hash function, which will give me the index of the number to be put on. So for example, I put the 12 in the second index, and then the 10 in the first index, right? So that's hashing. Collision means that, for example, I got this 5 and it also generated the same index as 12, which is 2, right? Now in this case, we can't put 5 in the 12th place where already 12 is lying there. So what we instead do is we use some techniques, and this is the process of collision, and we use some techniques to kind of minimize it and kind of mitigate it. So the first technique we use is linear probing, where we move the number by one step, and if that number, for example, I want to put the 4 again, or the number like 41 again, it's here. And now, for example, 9 generate the same index as the 41. Now I can say that I will move on to the above index, okay? So if I need to add a value at the end, I need to move it to the first index again, right? And then I can again check on if there is any space available. In this case, there's not any space available, but if you have a big hash table, it will be. And we will see that how this is going to be the main disadvantage of this technique, okay? So this was a little bit of introduction. Let's work on an example now. We have some sequence, and we want to see the indexes of where does this sequence goes. We have this whole, I think there are like 11 elements. So we are going to write them here: 12, 10, 0, 5, 9, 12, 25, 0, 5, 9, 12, 25, 41, 10, 3, 5, 7, 9, 41, 10, 3, 5, 7, 9. Right. Now I have these here, and now I want to use linear probing to kind of, solve this problem. And how we're going to do this, we're basically going to have some expression like x mod some value, right? Right, so this is going to be basically the hash table size or hash array size or whatever, but the question I'm solving for, it was given to be x mod 5, which was the hash function basically here, and we were using the linear probing to resolve our solution, right? And it has this 15 elements there, right? So this is going to be some hash function, which is going to be given for you so that you can start finding the indexes of each of these numbers, okay? So it is x mod 5 means we need to find the, and you will see that this function will map these numbers into the respective indices. Now we will do for each of these ones, we will write for each of these, we'll write x could be 12 mod 5 and 10 mod 5 and 0 mod 5. Then I have like 5, 9, 12, 25, 5, 9, 12, 25, 41, 10, 3, 5, 7, 9, 10, 3, 5, 7, 9. So now we can guess the answers. Okay, and let's go with the answer. So 12 mod 5, and what is mod basically? So it's a remainder when you divide 12. Something to the left should always go inside the bracket or inside your divisor. And then you have 5, so 5 2s are 10 because 3 becomes 15 and that's bigger. And whatever is the remainder, we're going to put it as the answer here. So for the 10, the remainder will be 0 because 10 is completely divisible by 5, right? Also the factor. 0 mod 5 means 0, 5. So if we have something like this, we will say 5 zeros are 0, and then we get the 0 back, right? It's better to just put it as a 0 here. It's more like, different variable here. So, and now we have 5 mod 5. That will also be 0 because 5 is completely divided by 5. And then 9 mod 5 means 9, 4. That would be like 4. And then for 12, it's again 2. For 25, 0 because it's completely divisible. For 1 because 41, 5 is a 40 and 1 is the remainder, 0. For 3, we will start doing it. 3, 5, 0 are 0. And then we get 3 here. And then we have like 5, so that's 0 again. 7, so that's 2. And 9, that's 4. Right? So we kind of got the indices for each of these numbers, and now we will see how can we arrange them into the indexes. So we formed the indexes, and now we will see how can we arrange them, right? So let me see here. So let me see how many indices we need to be having. Okay. So now, based on the numbers, so because they all need some index to be loaded at 0, 1, 1, 2, 3, 4, 5, 13. So like 13 elements. I will make an array so I can put these elements in. I'm assuming them to be 13. There could be more. Sorry for the 2, 3, 4, 5, 6, 7, 8, 10, 12, and 13 here. Just assuming, I'm not sure really. So okay, and then I'm gonna mark the index here. I should have made it 0, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Alright, so because there were a total of 13 elements and the index basically starts at it starts at 0, so I would assume it will go from 0 to 12. Okay, so for the first element, it was at the 2 index, so we'll put 12 into the second index, which is 2. Second doesn't mean 1, basically, it means 2 in this case, which is basically the third index. Then we'll go for 0. So 10 comes here, and then now 0 is also in 0, but we will not put it in 0 because in 0 there is already 10, so we move to the next one and put the 0 there. Now we have 5, right? So 5 is also in the 0th index, but we don't have 0th index anyway, so we'll put the 5 here because this is a space after the 0th, which is available space. 9 would go to 4, and then we have 12, which is again set to be in the 2 path, but it is going to be in the 5 because that's the available spot after 2. And then 25 is going to be 0, but eventually will fall here because all these slots are already filled. And then 41 will go to 1, same thing, it's need to be here because all the other slots are filled. 10, 3, all of them are filled. So 10, 3, 5, 7, 9. Because all of them was like 0, 3, 0, 2, 4. So as we can guess that they are already in the index, right? They are already going to be in the last part because we have already filled the earlier slots. So I wrote them in the sequence, right? So this is the actual index of them on hash table, more like a bridge than an array. But this is going to be my hash table, basically where each of these elements are going to be in the index. And we can also refer back 10 or 12, 5, 9, 12, 25, 41, 10, 3, 5, 7, 9, right? We have like 12 indexes, and the 12 indexes starting from 3, 5, and the 4, 9, 5, 12, 6, 25, 7, 41. So this was linear probing. We just use the function and find, the indexes, and then we put those indexes but the main point was to always move one step, means to the available slot, not necessarily the one step, but to always choose the one slot after this number, right? The number means, for example, I wanted to say I want to go for 0, but I didn't have any space for 0, so I go for 1. But if I didn't have any space for 1, I would go for 2. If I didn't have any space for 2, I would go for 3, right? So this is how linear probing works.